السلام عليكم ورحمة الله تعالى وبركاته. In this video, we're going to talk about derivative function. Derivative function. One, definitions. Definition one. So let's f be a function defined on AB, open, on an interval AB open. We say that f is differentiable on AB if it is differentiable on all elements belongs to AB. To the open interval AB. Let's take an example to understand this definition. Example. Let's take an f(x) equals x squared. We want to know if this function is differentiable on R. For that, let's take an element A belongs to R. Limit when x tends to A of fx minus fa over x minus a. That equals to limit x tends to a of the image of x is x squared, the image of a is a squared, fa is a squared over x minus a. As you can see, this is a remarkable identity. It's factorized on the form of x minus a times x plus a over x minus a. We can now simplify by x minus a. We'll find that the limit is, if we replace x by a plus a is 2a. And this number belongs to R. So f is differentiable on or at a belongs to R for all a belongs to R. For all elements belongs to R, we can say that f is differentiable at a. That means let f be a function. Let f be a function defined on an interval AB. AB is closed. So, in order for f to be differentiable on AB closed, if it is differentiable on AB open and differentiable on the right at E and differentiable on the left at B. We say it's differentiable on the right at E because we cannot approach A from the left, only from the right, because there is no value on the left of A. Same thing for B. We cannot approach B from the right, so only from the left. Let's take another example. Let's say, for example, let's study the differentiability of fx equals root x on the interval 0, 1. In order to study the differentiability of fx equals root of x on 0, 1, we need first of all to study the differentiability on 0, 1 open. So let's take an element A belongs to 0, 1 open. The same, we need to calculate the limit when x tends to a of fx minus fa over x minus a. And this limit should be a finite limit. It should be a number that belongs to R. Limit x tends to a, fx is root x minus root a is fa over x minus a. If we multiply this limit by the conjugate, fx minus fa over x minus a equals limit of x tends to a. The conjugate of root x minus 1 is root x plus 1. So we need to multiply root x minus root a by root x plus root a over x minus a times root x plus root a equals to limit x tends to a root x squared minus root a squared over x minus a times root x plus root a. This is equals to limit x tends to a of x minus a over x minus a times root x plus root a. Now we can simplify by x minus a, and we will find the limit of x tends to a of 1 over root x plus root a. If we replace now x by a, we'll find that this limit is equal to root a plus root a, which is 1 over 2 root a. So 1 over 2 root a belongs to R, implies f is differentiable on 0, 1 open. Now we need to study the differentiability on the right of 0. So we need to calculate the limit of x tends to 0 on the right. X is more than 0 of fx minus f0 over x minus 0 is the limit when x tends to 0 plus x more than 0 is noted by 0 plus. Fx is root x. F0, if we replace 0 in the function fx, we will find root 0, which is 0. X minus 0 is x. We do the same thing as previous limit. We need to multiply by the conjugate, and we know that the conjugate of root x is root x over x times root x. We will find the limit of x tends to 0 plus root x times root x is x over x root x. We can simplify by root x, and we will find the limit of x tends to 0 plus 1 over root x, which is plus infinity, 1 over 0 plus. So f has no limit, has an infinite limit and 0 plus, which means that f is not differentiable at 0 on the right. Now we need to study the differentiability of f on the left of 1, because we have a closed interval in 0 and 1. So we need to calculate the limit when x tends to 1, x is less than 1, of fx minus f1 over x minus 1, which is the limit of x tends to 1, x is less than 1, of root x minus f1 is root 1. Root 1 is 1. So minus 1 over x minus 1. Now we will multiply by the conjugate of root x minus 1, x minus 1 times root x plus 1 over x minus 1 times root x plus 1. The root x minus 1 times root x plus 1 is root x square, root x square minus 1 square over x minus 1 times root x plus 1. Limit of x tends to 1 minus root x square is x. 1 square is 1 over x minus 1 times root x plus 1. We can now simplify by x minus 1, and the limit will become x tends to 1 minus 1 over root x plus 1. If we replace now by 1, we will find 1 over root 1 plus 1, which is 1 over 2. Belongs to R, so f is differentiable at 1 on the left. Conclusion: f is differentiable on the interval open at 0 and closed at 1. Why is open at 0? Because we found that f is not differentiable on the right at 0. Definition number 3. Now let's define the derivative function. let f be a differentiable function on I, on an interval I. The function that connect every element x from I by its derivative number by f prime x is called the derivative function. Is called the derivative function. And noted by f prime. For example, the derivative function here, the derivative function of x squared is 2x. So we can now say that f prime x, the derivative function of x squared, is 2x for all x belongs to R. It's defined on R. In the other example, we take the root x and we found 1 over 2 root a. So the derivative function of root x is f prime x equals 1 over 2 root x for all x belongs to 0, 1, open at 0. Second part, let's take a look about the operations on the derivative functions. Let f and g be two functions. Differentiable on I, and we need the constant belongs to R and n belongs to n star minus 1. The first property of the operations is the derivative of the sum f plus g prime. If we apply the derivative on the sum, we will find f prime plus g prime. So the derivative of the sum is the sum of the derivatives. Second property, the derivative of alpha f constant times f is alpha f prime. The third property is derivative of the product f times g prime is f prime times g plus g prime times f. As you can see here, we switch the prime between f and g. Derivative of 1 over g is minus g prime over g squared, such that g is not equal to 0 on I. Finally, the derivative of f over g is f prime times g. We'll switch the derivative between f and g, but in this time with minus g prime times f over g squared. Third part, the derivative of some functions. The constant k belongs to R. Function is constant. For example, fx equals 2 is a constant function. Its domain is R, its derivative is 0, and domain of 0 is R2. So if we have a constant function, its derivative should be 0. Derivative of ax, such that a belongs to R. Derivative of ax is a. Domain is always R, because there are polynomials of degree 1. In general, if we take the function x to the power n, it's defined on R, and its derivative is n x to the power n minus 1. If you can remember, we take a function fx that equals to x0, and we found that f prime x is equal to 2x. If we apply this formula directly, we'll find the same results. So if we apply the formula, f prime x is 2, that's mean n, 2, times x of the power 2 minus 1, which is 2 times x. Domain of definition of nx minus 1, n minus 1, is R2. I forgot something about the operations here. Forgot about the exponents. Derivative of f to the power n is n f prime times f. N f prime times f. The derivative of 1 over x, domain of definition of 1 over x is r star, and its derivative is minus 1 over x squared. If we apply the operation 1 over g prime as previous is minus g prime over g squared. If we apply this operation on 1 over x, we'll find that the derivative minus the derivative of x over x squared. We know that the derivative of ax is a. So 1x is 1. So it's minus 1 over x squared. Derivative of root x. So root x is defined on r plus. Its derivative as previous exercise or example is 1 over 2 root x, which is its domain of definition is r plus star. Derivative of sine x, domain is r, and its derivative is cosine x. Derivative of cosine x, defined on r, and its derivative is minus sine x. Minus sine x. Domain of definition is also r. Now, we need to calculate the derivative of tangent x. The domain of definition is in the form of r minus pi over 2 plus k pi, such that k belongs to z. Because tangent of pi over 2 is not defined. Now, if we want to calculate the derivative of the tangent, all we need to do is write the tangent in the form of sine x over cosine x prime, and we need to apply f over g prime. F over g prime, as we know, is f prime times g minus g prime times f over g squared. If we apply this on the sine and cosine, so sine x prime times cosine x minus derivative of cosine x prime times sine x over g squared, that's mean cosine square x. The derivative of sine x is cosine x, so cosine x times cosine x, and the derivative of cosine is minus sine, so it's going to be plus sine x times sine x over cosine x squared. Cosine x times cosine x is cosine square x plus sine square x over cosine square x. We know that cosine square plus sine square is equal to 1, so 1 over cosine square x. So the derivative of the tangent is 1 over cosine square x. Or we can do another thing. And this, it's cosine square x over cosine square x plus sine square x over cosine square x, which is 1 plus tangent square x, or 1 plus tangent square x. Its domain of definition is the same as previous, so it's r minus pi over 2 plus k pi such that k belongs to z. Thanks for watching. I hope you enjoyed the lesson.